In this session, we will discuss about nucleophilic substitution reactions of haloarenes. Nucleophilic substitution reactions of haloarenes are extremely difficult. Here are some following reasons for extremely difficult nucleophilic substitution reactions in haloarenes. First reason, we can consider the resonating structures. Take example of chlorobenzene, in which there are non-bonding electron present on chlorine atom. So, if we draw the resonating structure, then resonating structures are as follows. Now, this will move here and this will move here. So, another structure we will get like this. Next structure, and in the last structure, so these are the resonating structures possible in chlorobenzene. Now see here that there is double bond character developed between carbon and chlorine, and because of this it is not an easy task to break this bond. So this is one reason. Second reason, we can consider hybridization. What is hybridization possible in haloarene? In haloarene, we have sp2 hybridization as compared to haloalkane like CH3Cl. There was sp3 hybridization. So S character is more, and because of that more electronegativity, again we say more energy is required to break this bond. Second thing we can consider, the bond length, CH bond length, that is CCl bond length, is only 169 picometer, whereas it was 177 picometer in the case of CH3Cl, that is alkane. So if the bond length is shorter, it is not easy to break that bond length. Third is instability of phenyl cation. Phenyl cation developed because of self-ionization. This cannot be stabilized by resonance. And fourth point is repulsion. We have two things. One is electrophile, that is rich in electron, and we have arene, nucleophile, that is also rich in electron, and we have arene, that is also rich in electron, and because of that repulsion is possible. So because of all these four reactions, nucleophilic substitution reactions in arenes are extremely at a slow rate. Even then we will study some reactions, that is nucleophilic substitution reactions in arenes as follows. Again, chlorobenzene, when it is reacted with NaOH, 300 atm pressure and 623 Kelvin temperature. It gives phenol. So chlorobenzene has been converted to phenol. First step is this and second step is mineral acid, that is hydrolysis. Chlorobenzene converts to phenol. This is also known as a Dow process. We can see the temperature is 623 Kelvin and atmospheric pressure is 300 atmospheric pressure. So chlorobenzene can be converted to phenol, but the condition is vigorous, means high temperature and high pressure is required. But NO2 group is present, that is electron withdrawing group is present in chlorobenzene. Then the same reaction will take place, but the temperature will become low, that is only 423 Kelvin. And we are getting the product, that is phenol. If more NO2 is produced in chlorobenzene on ortho position, here it was on para position, here now it is on ortho as well as para position, then we can complete the reaction even at a lower temperature like 368 Kelvin. So here also two steps are followed and here also two steps are followed. But remember, we could minimize the condition and we are getting the product. Now, if nitro group is produced or introduced at all the three positions, ortho, para and again this ortho position, then this reaction is completed just by using warm with H2 will give OH, NO2, NO2, O2N. See, if we have 3 nitro group with chlorobenzene, then chlorobenzene can be converted to phenol by using just simply with the reaction with warm H2. Now, few more reactions we will study. And remember one thing, that if NO2 group is at meta position, if NO2 group is at meta position, there is no change in the rate of reaction. Now we will study some more reactions, but that will be electrophilic substitution reaction in haloarenes. We will take example of chlorobenzene. Chlorobenzene, as we know that because of the incoming group chlorine, the next product will be of 2 because of chlorine group is ortho and para directing. So we will get 2 different products. First we will take the example of chlorination. Chlorination is done in presence of Lewis acid like FeCl3. So if chlorobenzene chlorination takes place, we get 2 different products, ortho dichlorobenzene and para dichlorobenzene, that is 1,2 dichlorobenzene, or we can say ortho dichlorobenzene, and this is para dichlorobenzene, or 1,4 dichlorobenzene. Remember, 1,4 dichlorobenzene is major product. So chlorination, we are getting 2 different products, ortho as well as para. Now think for nitration. Nitration of chlorobenzene takes place in presence of concentrated HNO3 plus concentrated H2SO4. So because of the reaction between concentrated HNO3 and concentrated H2SO4, electrophile produced is NO2 positive. So we will get again two products, chlorobenzene, NO2 group at ortho plus chlorobenzene, NO2 at para position. So 1 nitro chlorobenzene, 2 nitrochlorobenzene and 4 nitrochlorobenzene. 1 nitrochlorobenzene and 4 nitrochlorobenzene. 2 nitrochlorobenzene and 4 nitrochlorobenzene. Now we will discuss another electrophilic substitution reactions in chlorobenzene. Taking example of sulfonation, of chlorobenzene, fuming H2SO4, that is H2SO4 and SO3 mixture. This is known as fuming sulfuric acid. When chlorobenzene sulfonation takes place, there are two possible isomers, ortho as well as para. So SO3H group will be introduced at ortho position as well as para position. Another reaction, that is alkylation, is also known as Friedel-Crafts alkylation. In Friedel-Crafts alkylation, CH3Cl and catalyst used is AlCl3. Because of CH3Cl and AlCl3, the electrophile produced is CH3 positive. Again we will get two products, chlorobenzene with methyl group. So name of these two products, one is ortho, one is para. Orthochlorotoluene, and para-chlorotoluene, or we can say 2-chlorotoluene and 4-chlorotoluene. One more reaction possible is acylation. CH3COCl, acetyl chloride and AlCl3. The electrophile produced because of CH3COCl and AlCl3 is CH3CO. So two different products, CH3 ortho product plus para product. But because of the more reactivity of COCH3, we will have the name like 2-chloroacetophenone. And 4-chloroacetophenone. Now discuss about few more reactions, that is we can say reactions with matter. One is Wood's reaction. Wood's reaction already we had completed in 11th science also, but again look, if we have Rx plus 2 moles of Na, in Wood's reaction we take 2 moles of Rx, that is haloalkane, and 2 moles of sodium. In presence of dry ether, we get alkane, corresponding alkane, and removal of 2NaI or 2NaX we can say. But if we consider about Wood's fatigue reaction, in Wood's fatigue reaction, chlorobenzene plus sodium and plus chloromethane. So sodium and chlorine will be removed as 2NaCl again in dry ether presence, and the final product formed is methyl benzene, or it is toluene. If simply we think for fatigue reaction, then 2 moles of haloarene and 2 moles of sodium in presence of dry ether, we get biphenyl as a final product. So this is about fatigue reaction.